Good morning, everyone. I hope you're enjoying your snow day. We're not doing this entire section. We are just doing some parts of section 2.1 because we'll cover a lot of the material that would normally be taught in 2.1 just in section 2.2. In this section, we're discussing systems of two equations. A system of two equations and two variables are used to answer questions which involve two different variables and some constraints on what those values can be. It's fairly simple to solve systems of two equations, but when the systems get larger, like three equations with three variables, it gets more complicated, and we'll handle that in section 2.2. I want to also say that we have seen this before when we did supply and demand back in section 1.2 when we learned equations of lines. We solved systems of equations by graphing and by elimination. So here we'll discuss it a little bit more formally. In this section, we'll discuss systems of equations, solving just by substitution and elimination. We'll skip the echelon method. So looking at what I mean by a system of equations, it's when you have a set of n linear equations, and again, remembering that linear, means that you have lines. So if there's n equations, you also want to have n variables. The two most common that we will deal with are two equations with two variables, which, for example, would look something like this. You have a first equation, 2x plus 5y is equal to 9, and a second equation, negative x plus 4y is equal to 7. You can also have a system of three equations with three variables. For example, 2x plus 3y minus 6z is equal to 8, negative 3x plus 4y plus 8z is equal to 9, 5x plus 9, oh my, I've never noticed that typo before. This is a 9y plus z is equal to negative 1. These are linear equations because they're all the general form of a line. Now, we're looking at solving a linear system. A solution of a system means the values for all the variables in the system that make all of the equations true simultaneously. So the values of x and y will work in both equations, and if you have x, y, and z, the values you get for x, y, and z will work in all three equations. There are three possible types of solutions. You can have two lines that intersect. So again, this is what would happen in section 1.2 when we looked at supply and demand and we plotted the two graphs and found their equilibrium point by finding their intersection point. The first thing that can happen when you have equations and you're looking at a system is that they can intersect in one point. When that happens, this is called, you have one solution. Systems of this type are called independent. Alternatively, you can have, well, let me draw that first, sorry. Here's line 1. Here's the other line. They intersect in this point. That point lies on both lines, so it's a solution to the red line and it's a solution to the blue line, so it makes both equations true at the same time. That system is called independent. The second thing that can happen is that you can have two lines that never intersect. I'm hoping you might recognize two lines that never intersect means that they must be parallel. If they never intersect, there is no solution. They are parallel lines. When this happens, the system is called inconsistent. Take a second to think about this. The solution to a system are the values of x and y that work in both equations. If I have two parallel lines, there is no point on line 1 that would also lie on line 2 because the two lines never meet. They have a completely different set of points that make the equations work, so there is no ordered pair that would work for both equation 1 and equation 2. The third thing that can happen is that your two lines are actually the exact same line. The lines overlap completely in all points. So what would that look like? Well, I would plot my first line. Sorry about that. And then the second line is exactly the same line as the first line, so it's lying on top of the first line. If the two lines are exactly the same line, that means you would have a dependent system. So if the two lines are the same, this means there is infinitely many solutions. I don't know what I just did. The lines overlap completely in all points. This system is said to be dependent. Now, the first way you can solve a system is by substitution. Graphically is the easiest way to interpret how to solve a system, but if your system happens to involve fractions, you will never get an accurate solution. So using a graph may not be the best way. We'll discuss two ways to solve a system. The first is by using substitution. The second will be by using elimination. You've probably seen these both before in high school, so I'm hoping this section is just a memory refresh. So moving to the next slide. The substitution method involves solving one of the equations for a variable and then substituting the result into the other equation. So here are two equations. 4x plus y is equal to 9. 3x minus y is equal to 5. We will solve this by using substitution, but I want to first begin by showing you the equation of these two lines graphed so we can identify again the interpretation and meaning of what a solution to a system is. The first line is a line with positive slope. So this line I suspect is 3x minus y is equal to 5. And then the other line should be the 4x plus y is equal to 9. They seem to intersect in some point. If only I could see better, I think that might be the ordered pair 2, 1. Let's see if I can zoom in and see. It's 2, 1. That point lies on both lines. But again, we're lucky because those points are whole numbers. The x value is a whole number, the y value is a whole number. There wasn't a lot of estimating going on, which you really don't want to do. You want to have an exact answer. So we're going to do this by substitution, which again I suspect you know. You begin by solving one of the equations for one of the variables. I think that I might have more space for this on the next slide, so I'm going to scoot on over. We want to solve one of the equations for one of the variables. I don't remember the equations, so I need to go back and get them. 4x plus y is equal to 9. 4x plus y is equal to 9. And the other is 3x minus y is equal to 5. So we're going to solve one of the equations for one of the variables. I would tend to opt to solve equation 1 for y. Think about y for a second. I'm about to substitute the variable into the other equation. The easiest variable for me to solve for is y in the top equation. I can get y alone by simply subtracting 4x on both sides. Now we will substitute, we're on to step 2, substitute that expression into the other equation. So here's equation 1 solved for y. I'm now going to take 9 minus 4x and place it into equation 2 for the y. Equation 2 says 3x minus y is equal to 5. I'm going to replace y with 9 minus 4x. Please remember to put it in parentheses because you are replacing a single variable y with a two-term piece, 9 minus 4x. So please put it in parentheses because now you will need to distribute this negative through. That will give us 7x minus 9 is equal to 5. The good news about this now is you end up with an equation that has only x in it. Now for some reason my notes don't continue on to tell you what to do next, but I'm hoping that at least it's obvious considering that we only have one variable now. We can add 9 to both sides and get that 7x is equal to 14, divide both sides by 7, and we get that x is equal to 2. There is a third step. You have to solve for the other variable using any equation you prefer. Since the solution should work in the original equation 1 or the original equation 2 or the solved for y equation, you can use equation 1, equation 2, or the alternative of equation 1. It doesn't really matter which one you choose. Now, I will tell you that the easiest is this one. That's because I now know the value for x, it's 2. I can simply substitute that number 2 in for this x right here, giving me the value for y. So y equals 9 minus 4x. I know that x is 2. Y will equal 9 minus 8, and we get that y is 1. Do you remember what the graph told us the solution would be? Let's go back and look.